Hello and welcome to the fourth part of this talk on oxygen, haemoglobin and blood. My name is Dr. Budnaniakara, respiratory and sleep physician at Orange Health Service, as well as lecturer in medicine at Charles Sturt and clinical lecturer in medicine at University of Sydney. So you should now all know that oxygen is vital for human functioning, as it helps to produce the sufficient quantities of ATP required through aerobic respiration. You should also know that the cardiorespiratory system helps to bring oxygen from the environment into the lungs, into the circulatory system, and thence onto the tissues, where oxygen is utilized by the mitochondria to produce ATP. The last part of our talk, we explored the reason why oxygen was poorly soluble in blood, and we explained the necessity to have a hemoglobin molecule that can carry sufficient quantities of oxygen in order to deliver it to the tissue such that it can be used to produce ATP. So in this section of the talk, what we're going to do is we're going to explore the molecular structure of hemoglobin in great detail. We're going to see how it can deliver oxygen. We're going to talk about a new concept called the oxygen dissociation curve. And we're going to see some of the physiological effects that modify this curve and how it all fits in quite beautifully with regards to human evolution. So, the first thing to note is that hemoglobin is nearly found in all of the animal kingdom, particularly in the vertebrae, and there's only one animal that lacks this, and that's the Antarctic ice fish. So it was in 1928 that a biologist known as Rustad, he was traveling down this region and he caught this fish, and he found that this fish was really odd. He called it the white crocodile fish. He said he had large eyes, he had long toothed snout and diaphanous fins. What he did was, let me just go back here. What he did was he cut the fish open, and what he found was that the blood of the fish was colourless. He's described it as not a drop of blood everywhere, and you can see here, it's completely clear. He also found that his gills were soft and white, and it was rather than dark as wine in comparison to its nearest evolutionary neighbour, the cod. It was living at a constant temperature of minus 1.9 degrees Celsius, and itself had an oxygen carrying capacity of less than 10%, simply because it lacked hemoglobin. So how did it do so? Well, because it lacks hemoglobin, it needs to be able to carry sufficient oxygen in order to meet its metabolic needs. It cannot just survive on anaerobic respiration. So what it turns out is that these ice fish have huge hearts that are able to pump vast quantities of colourless blood to the circulatory system. This colourless blood, of course, is devoid of hemoglobin, so oxygen is dissolved within the blood. It's also known that the water in the oceans in Antarctica, particularly in this region, have a high oxygen content, and that's because the temperature is so cold. And the reason why that's important is that as temperature increases, the solubility of a gas decreases. So there's a temperature dependence of solubility. And if you think about it, it kind of makes sense. So if you increase the temperature of a liquid with a gas in solution, what you're doing by increasing the temperature is you're increasing the kinetic energy of the molecules. And by increasing the kinetic energy, you're causing a lot more random collisions, and you can imagine you're going to increase the kinetic energy of the gas molecules, and they're going to pop out of solution back into the gaseous phase, where essentially they belong. So when you have a cold environment, it follows also that the solubility of oxygen is going to improve. So these waters have a high oxygen content, and they're not as, so the solubility is improved of oxygen. Also, what's found was that the currents around where these fish live, which is near South America, is that the currents trap the fish there and they prevent other fish from getting in. So they live in an evolutionary niche. And also, it probably what happened was there was an accidental gene deletion which codes for the protein, the globin protein, that encodes for haemoglobin. And these fish, as mentioned, have very large hearts. So I've circled the heart there, and you can see it's nice and tan rather than red, rich of haemoglobin blood. It's got big vessels, and it's also got slow metabolism. So the basal metabolic rate doesn't require as much oxygen. So let's focus a bit more in detail of the haemoglobin molecule, because we really need to understand that to kind of understand the molecular physiology underpinning its carriage of oxygen. So hemoglobin essentially consists of 5 parts. Firstly, there are 4 globin chains. Now globin is simply a protein with a specific structure. And for hemoglobin, there are 2 alpha and 2 beta chains. Now the alpha chain has 7 helices. So a helix is a specific structure that a protein associates into. It's kind of like this. We call them an alpha helix. So the alpha chain has 7 helices, and the beta chain has 8 helices. And essentially they fold upon each other with a pore in the middle, and within that pore sits that protoporphyrin ring, which is over here. And that protoporphyrin ring, if you can remember from the previous structure, has an iron molecule in it, which is just over here. And that iron molecule complexes oxygen. So it's arranged nice and neatly within the hemoglobin molecule. Now, there's a protoporphyrin ring with an attached iron and a complexed oxygen when it's oxyhemoglobin to each of these 4 subunits. So we'll have a protoporphyrin ring here, 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 and here. And so each hemoglobin molecule, which is a tetramer consisting of 2 alpha and 2 beta subunits, each has a carrying capacity of 4 oxygen molecules. Now it so happens that an alpha and beta come together as a dimer, and so the 2 alpha beta dimers come together to form a tetramer. Oops, sorry about that. So how does oxygen come in to hemoglobin? Well, it so happens that we have a nice curve to describe this, and that's called the oxygen hemoglobin dissociation curve. And that relates to the partial pressure of oxygen and the percent saturation of hemoglobin. So let's have a look at this. So remember, at 100 millimeters of mercury, that's the partial pressure of oxygen within the pulmonary capillaries that is diffused down its concentration gradient from the alveoli. So that's partial pressure of oxygen in the pulmonary capillaries. You can see that this corresponds to a hemoglobin saturation of about 97%. So at a partial pressure of oxygen of 100 millimeters of mercury in the pulmonary capillaries, 97% of the hemoglobin of the 140 grams per litre that's normally there is completely saturated with oxygen. And remember, a fully saturated haemoglobin molecule can carry 1.39 mils of oxygen per gram of haemoglobin. That's when it's 100% saturated. Let's talk a bit about this curve in a bit more depth. So, one of the striking things about this curve is that it's not linear, it's sigmoidal. And what you can see is that as the partial pressure of oxygen increases, there is a much steeper rise in the amount of haemoglobin that's saturated until we get to a plateau. And the reason behind this is cooperativity. Essentially, what happens is when one oxygen molecule binds to that protoporphyrin ring in a subunit of haemoglobin, it makes it much easier for the other oxygen molecules to bind. There's cooperativity, and we'll explore a bit more in detail in terms of the molecular physiology behind this. So we can see as two molecules have joined, it's much easier for the third molecule to join. Whoops. And it's much easier for the fourth molecule to join. Now, this cooperativity is fundamental to understanding the oxygen hemoglobin dissociation curve. Okay, so to further understand the molecular rationale behind cooperativity, we need to have a look at these diagrams and what happens when an oxygen binds. So when an oxygen binds, essentially what occurs is that you can see here, so this is hemoglobin without oxygen, which we call deoxyhemoglobin. And when oxygen binds, what happens is this protoporphyrin ring moves into the plane of the ion. So it's moved into the plane. And it's what scientists call it's moved from a tense state to a relaxed state. And essentially what happens is when the protoporphyrin ring flips into plane, it causes the actual globin molecule to move. And when it causes the globin molecules to move, that opens up the pore that makes it more and more accessible for oxygen molecules to occur. And you can see in this cartoon here the hemoglobin is without oxygen, so it's deoxyhemoglobin. And what you can see here is the pore is quite narrow, so oxygen hasn't associated with the protoporphyrin ring here, which is buried within the globin chain. When one oxygen molecule has joined, that causes the protoporphyrin ring to fall within plane of the ion atom. That changes the structure of the globin molecule, which subsequently changes the structure of the other associated globin molecules, and that makes it much easier for other oxygen atoms to join the protoporphyrin ring. It goes from a tense state over here and it goes to a relaxed state over here. And you can see, you can see that the molecules, so the pores have increased their size, so it's improved the affinity. And that explains why, as you go up the oxygen hemoglobin dissociation curve, the steepness of the curve increases, and that's because of cooperativity. Remember, hemoglobin goes from the T state, where it's tense, that's the deoxyhemoglobin, and it goes into the relaxed state, which is the oxyhemoglobin. Now, I hope that makes sense. Let's have a look at a couple of other points on the oxyhemoglobin dissociation curve. So, one point to kind of remember is the partial pressure of oxygen at which the hemoglobin saturation is 90%. And that's partial pressure is about 60 millimeters of mercury. Now that point's important to realize, because what happens is, if you can imagine, if the partial pressure of oxygen drops a bit more, then there is a much rapid fall in the oxygen saturation of hemoglobin. And that has significant impact, because if you imagine, if you're on the steep end of the oxygen hemoglobin dissociation curve, you're going to have markedly less hemoglobin saturation, and that's going to significantly reduce your carriage of oxygen, or your delivery of oxygen. Remember, oxygen is mainly carried in hemoglobin. It's very, very poorly soluble in blood. Remember the solubility coefficient of 0.003. Another point to remember is called the P50, which is the partial pressure of oxygen at which the hemoglobin saturation is 50%. And the importance for this is that it can help to define the affinity of the individual hemoglobin dissociation curve. And let's have a look at this. Suppose instead of this blue curve here, we have this green dashed curve that's grown here. If you take the P50 of the blue curve as before, the P50 is about, let's just say, 27. Now if we take the same point on the green curve, which has been right shifted, what we can see is that the P50 has increased, let's just say, to about 44 millimeters of mercury. So as the P50 increases, the affinity of the hemoglobin to carry oxygen has dropped, and that kind of makes sense. So the importance of this, and this is always examinable, not only in medical school, but throughout your medical career. When you go into specialist examinations, you're bound to get a question on the hemoglobin oxygen dissociation curve. The reason why this occurs is that there are a few what we call allosteric modulators that shift this curve, and we'll go into the details of this in a bit further. Firstly, protons. So hydrogen ion concentration, which is essentially acidity or pH. If you increase your hydrogen ion concentration or you decrease your pH, that causes a rightward shift to the oxygen hemoglobin dissociation curve. It increases the P50, therefore decreases the affinity of the hemoglobin to oxygen. So too does increasing carbon dioxide. So too does increasing 2,3-DPG, which is a intermediate of glycolysis, and we'll go into this in a bit more detail. And so too does increasing temperature. And again, we'll touch on this, but suffice to say, it is advantageous to have a right shifted hemoglobin dissociation curve if you want to unload oxygen. Because if you think about it, it is no good that oxygen is stuck to hemoglobin. We certainly need it. We certainly need hemoglobin there to transport the oxygen. But once it gets to its tissues, we really need to unload the oxygen. We can't just keep it there, because it's no use. It has to get into the mitochondria where it can participate in oxidative phosphorylation electron transport chain to generate that ATP. So in the periphery, if we can shift our hemoglobin to be a bit more graceful in giving its oxygen away by decreasing its affinity, that would be advantageous. Also, in the lungs, we want to take up oxygen. We want our hemoglobin to be to tightly take up oxygen. We want to transport it. We don't want to give it away. We want to get it from the lungs. We want to get it from the alveoli. So in the lungs, it would be advantageous to have a hemoglobin oxygen curve that's left shifted, right? Which would have a lower P50, and therefore have higher affinity. And things that cause a left shift is essentially the opposite of things that cause a right shift. So decreased temperature, decrease 2,3 dpg, decrease carbon dioxide. That's what happens in the lungs, right? So in the lungs, it will be a low CO2 environment because we're breathing it out, as well as decrease H plus or increase pH. It's the same thing. Now let's explore this in detail. So let's have a look at the effect of carbon dioxide. Already I've explained that carbon dioxide causes a rightward shift of the oxygen hemoglobin dissociation curve. And the way it does that is because carbon dioxide binds to amino acid groups on the hemoglobin. So remember, the hemoglobin has 4 units, so it's a tetramer. Each of these units carry a protoporphyrin ring, each having iron. Each have the ability to complex oxygen. Okay, so what carbon dioxide does is it binds to various amino acid groups in the hemoglobin molecule, and by doing that it causes a conformational change that favors the tense hemoglobin configuration, the configuration where it was harder for oxygen to bind hemoglobin. So in the presence of carbon dioxide, hemoglobin is more likely to be in the tense state and therefore in a deoxygenated state. The reverse is also true. In the presence of oxygen, it is less likely for hemoglobin to be able to carry carbon dioxide. Now let's see the functional significance of this. But to me it kind of makes sense. So in the lungs, in the presence of oxygen, we want to be able to offload carbon dioxide. We want to be able to kick out the carbon dioxide from the hemoglobin molecule so that the carbon dioxide can diffuse out from the pulmonary capillaries down its concentration gradient into the alveoli to be exhaled. So it would make sense that having that loading oxygen into hemoglobin in the lungs should be able to reduce the affinity of hemoglobin for carbon dioxide, helping to kick carbon dioxide out and for us to breathe it out. Also in the peripheries, remember, tissues are actively metabolizing, they're requiring oxygen, and by the process of aerobic respiration, remember, we're producing carbon dioxide. Remember, glucose plus oxygen gives carbon dioxide and water plus a truckload of ATP. So we produce carbon dioxide, and that's mainly through the Krebs cycle. We want to transport that out, so that can either be dissolved in venous blood, it can be combined to bicarbonate, and we don't need to know this in great detail, but suffice to say we'll talk about this further in lectures to come in our respiratory block. But it can also be combined with hemoglobin, and this is what happens. So in the presence of carbon dioxide, we want to get rid of the oxygen in the hemoglobin, we want to unload it to tissues, that's physiological, and carry the carbon dioxide so we can breathe it out. And let's have a look at this graph here, right on the right. So this is the carbon dioxide dissociation curve, and this is a little bit tricky to understand, but I want you to just bear with me to go through it. So what happens here is that as we've got the red line is arterial blood. Now as the carbon dioxide levels increase, so we go from lungs where obviously the carbon dioxide levels are low, and then we go to the tissue where the carbon dioxide levels are much higher. That makes sense. Remember, the tissues are actively respiring. So the carbon dioxide content in the blood increases, and we can see here on the y-axis, that's the carbon dioxide content. Now, when we get into the tissue, remember the carbon dioxide's given, it combines with hemoglobin, and it kicks off the oxygen. Oxygen diffuses down to the mitochondria where it can do work. So the carbon dioxide content, for the same partial pressure of carbon dioxide, the carbon dioxide content now increases. And it increases so in venous blood. And you can see that step up, that blue line is venous blood. And then when we get to the lungs, where the partial pressure of carbon dioxide is low because we're breathing it out, oxygen's there, that's coming in from the alveoli into the pulmonary circulation. This kicks off the carbon dioxide, it reduces its affinity to carbon dioxide, and therefore the carbon dioxide content drops in arterial blood. Now, I hope that makes sense. Now, what this is called is the Haldane effect, a very important effect in physiology. Okay. What about how protons work? So protons, H+, are positively charged cations. And what they do is essentially they disrupt structure because, amino acids, they have positive and negative charges, and they come together to form proteins of complexity. And by changing the proton concentration in the environment around it, it follows that it's going to break these bridges or salt bridges that have formed. So by changing the structure of the of the protein, what hydrogen ions do, or acidity in the form of pH, is it favors the tense state. So this is called the Bohr effect. So in the presence of an acidic environment, acid being a lower pH, being higher hydrogen ion concentration, hemoglobin is more likely to be in the tense state or the deoxygenated state compared to the relaxed state. That causes a right shift of the hemoglobin oxygen dissociation curve. And think about the functional significance of this. So in the tissues, just imagine you're going for a run, a hard run up a hill, and your quadriceps are burning. There's not enough oxygen in order to get the delivery of oxygen necessary to generate the sufficient ATP to get those muscles going. So you're starting to generate lactate through glycolysis. And that lactate causes an increase in acidity, drops the pH. Now, it would make sense that when the blood gets to this tissue, we want it to unload as much oxygen from hemoglobin as we want. We don't want hemoglobin to hold on to oxygen. We want to unload the oxygen. So it should make sense that in this environment, a lowered pH, high acidity, high hydrogen ion concentration, by changing the molecular structure of the compound itself, helps to right shift the hemoglobin oxygen dissociation curve, cause a decrease in affinity, increase the P50, and unload its oxygen. This is called the Bohr effect. I won't go through this in greater detail, but this is just to reference how hydrogen ions and carbon dioxide interact with hemoglobin to cause unloading of oxygen from the hemoglobin. Remember, high carbon dioxide causes right shift. That's Haldane effect. High hydrogen ion concentration, which is the same thing as reducing your pH, causes the same right shift, causes the Bohr effect. And very briefly, what you can see is in the tissues, when you're producing high carbon dioxide from aerobic respiration, that causes some of the carbon dioxide to chemically combine with hemoglobin to form carbaminohemoglobin. Remember, carbaminohemoglobin doesn't like to carry oxygen. It's in the tense state. It locks the hemoglobin in the tense state. And that kicks off oxygen to be delivered to tissues. Whoops. Some of this carbon dioxide, I'm very sorry about that, some of the carbon dioxide also forms bicarbonate, which is the majority of what carbon dioxide is carried, which then dissociates to form bicarbonate and a proton, which contributes to acidity. That proton combines with the hemoglobin, which locks it in the tense state, changing, kicking off the oxygen from the relaxed state hemoglobin or oxyhemoglobin to make it deoxyhemoglobin or tense state hemoglobin, causing it to lose its oxygen to be available for aerobic respiration in tissues. Have a look at this slide and see if it makes sense. What about the effect of temperature? Well, it so happens that the combination of hemoglobin and oxygen to oxyhemoglobin, which goes from the tense state to the relaxed state, that releases energy in the form of heat. That should make sense because hemoglobin in the relaxed state is it's much more calm. It's in a relaxed state, so it's lost energy to get there. Now, let's just say we add temperature. Well, to restore this equilibrium using Le Chatelier's rule from high school chemistry, we know that the equilibrium is going to change in such ways to restore it. And so what happens is if you increase the temperature by increasing heat, you're going to favor, again, unloading of oxygen from hemoglobin, because what you want to do is you want to reabsorb that heat to kind of restore equilibrium. And again, that kind of makes sense in the peripheries where we're actively metabolizing, we're actively generating heat. And so in these tissues, where we want to deliver oxygen, we want to unleash oxygen from hemoglobin to go into cells to participate in aerobic respiration. So I hope that all kind of makes sense. What about the effect of 2,3-DPG? Now, 2,3-DPG is a little bit more complex. Essentially what it is a glycolytic intermediate. It's a metabolic byproduct that accumulates in red blood cells. Now, it accumulates in all cells, but in red blood cells in particular, it likes to associate with hemoglobin. And what increased levels of 2,3-DPG do is that it causes a right shift. It increases the P50, decreases affinity for oxygen. And what leads to increased 2,3-DPG? Well, 2,3-DPG is increased by chronic hypoxia. So, in patients at altitude, it's also increased by metabolic alkalosis or intracellular alkalosis by low hydrogen ion concentrations within low hydrogen ion concentrations within the cell. What's also interesting about 2,3-DPG is that as the red cell ages, the 2,3-DPG content decreases. So older red cells have hemoglobins that are a bit stingy in giving oxygen because they're left shifted, because they have less 2,3-DPG. And the other thing is, when we store blood for transfusion later, after 14 days, the 2,3-DPG in stored blood is next to nothing. So you can see here, that's that curve there. The P50 is very small. It's less than 20. It's significantly left shifted. So red cells that have been stored for over 14 days are not good at unleashing the oxygen that is stored within the haemoglobin. So, I hope that makes sense. I hope I have spoken to the molecular physiology of haemoglobin. I hope I've explained how the various components of haemoglobin come together to accept oxygen. I hope the whole concept of tense state hemoglobin and relaxed state hemoglobin makes sense. Remember, tense state is deoxyhemoglobin. It's hemoglobin without oxygen. But once one molecule of oxygen comes in, remember it causes a conformational change in the globin structure that makes it much easier for other molecules of oxygen to come in. Remember that cartoon? And the hemoglobin goes from the tense state to the relaxed state. I hope the shift of affinity of hemoglobin makes sense, and I also hope that it makes sense that increased carbon dioxide levels decreases the affinity for oxygen, causes a right shift, and a right shift is also caused by increased acidity or decreased pH, as well as increased 2,3-DPG and increased temperature. If you can really understand those concepts, I really think you're doing well, and it'll pay you good stead for the future. Thank you very much.